Hi, my name is Sarah Appleby and I'm a PhD student working with Emil Dave and Daniele Serini. This is some work we've done recently looking at the low redshift CGM in Simba. In particular, we're focused on comparing H1 and metal line absorption in Simba to the COS-Halos and COS-Dwarfs surveys. So first to introduce Simba, this is more fully described in the Dave 2019 paper. They're cosmological simulations, and while I won't go into the full physics, I'll just highlight two of our key features. First, the black hole model, where we grow our black holes using a combination of torque-limited accretion and Bondi accretion, and then we have a physically motivated AGN feedback model. And then secondly, our dust model, where we produce, grow, and destroy dust throughout our simulation. So first we examine mass budgets for each of our halos. In the paper we also look at metal budgets and metallicities, but here we're just looking at the fraction of mass in each of these halo components as a function of stellar mass of the central galaxy. And this fraction is with respect to the cosmic baryon fraction. So at the low mass end, we see that these are mainly star-forming galaxies that have multi-phase halos containing cool, warm, hot CGM gas and ISM gas as well. And these galaxies are mostly affected by stellar feedback. Whereas when we go to the high mass end, these are mostly quenched galaxies that are dominated by hot gas in their halos. And these have been affected mostly by our jet mode feedback model. And then also we can notice that the baryon fraction is always less than 1 for all masses, and this is due to the baryons being evacuated by our jet mode AGN feedback. So next we compare absorption in Simba to the COS-Halos and COS-Dwarf surveys. To do this, we wanted to create an analogous matched galaxy sample from Simba to match the conditions of those surveys as closely as possible. So for each COS galaxy, we select 5 Simba galaxies that most closely match that galaxy in terms of stellar mass and SSFR, which is what I'm showing in this figure here is our Simba sample compared with the COS-Halos and COS-Dwarf samples. And then we also impose an isolation criteria so that there are no other central galaxies within 1 megaparsec of each of our Simba galaxies. And then we generate synthetic spectra using PyGAD and apply observational effects to try and mimic the parameters of those surveys. Here we show that comparison in terms of equivalent width between COS-Halos and COS-Dwarfs and our Simba samples. So each panel here shows a different ion, and each of the panels is equivalent width versus impact parameter scaled by the virial radius. So for COS-Halos, we're looking at H1, magnesium 2, silicon 3, and oxygen 6, and for COS-Dwarfs, we're looking at H1 and carbon 4. And for each of these, we see a reasonable agreement between Simba and these observations. In particular, our H1 measurements around star-forming galaxies are in really good agreement with the data, although there are some interesting discrepancies. For example, our quenched galaxies showed under-predicted H1 absorption. When we look at the metal lines, we find that our metal line absorption is really dependent on our choice of ionizing background, at least for our COS-Halos sample. And then another interesting thing is that we're reproducing the dichotomy that's seen in observations in terms of O6 between star-forming and quenched galaxies. Here we look at the impact of stellar and AGN feedback on absorption in the CGM by turning off and on various components of our feedback model. So when we start off with a model with no feedback whatsoever, we find that it has reduced absorption for all of these ions. And then with the addition of stellar feedback, that then enriches the CGM, and we see an increase in absorption for all of these ions. And then with the addition of AGN feedback, that then heats the CGM and then reduces the absorption, particularly around the COS-Halos sample, which are more massive galaxies. So here's my summary. Please do get in touch if you'd like to discuss anything, and I'd thank you for your attention.